Hi, my name is Yufei Xu. I'm a PhD student at Georgia Tech in the Computational Science and Engineering program. I'm working with Dr. Tennebaum and Dr. Pita on Project M3 of Multimodal Optimization and Simulation Track, MMOS integration. In this project, our goal is to understand the role of ride-hailing services in public transit ridership decline, given that ride-hailing is a competing service to transit. To do so, we develop a multimodal optimization model with a multi-agent simulation considering both transit and ride-hailing services. The objective of our work is to obtain a realistic representation of ride-hailing driver behavior towards generating a ride-hailing driver fleet for the simulation. With the supply and demand of public transit and ride-hailing services, we can understand the trade-off between these two services in the simulation. In this project, we leverage a unique dataset that includes transportation network companies' data from November to December in 2016 in San Francisco. The TNC dataset includes both Uber and Lyft data, as Uber data does not include unique driver identifiers. We cannot know which shift or trips are performed by which driver, so we use only the Lyft data to model driver behavior, and then we scale it up to also include Uber drivers. This dataset does not include any social demographic information about the drivers, but since we want to account for some of the heterogeneity in drivers' behavior, we included a driver type variable in our model. Based on this variable, we differentiate between full-time drivers, part-time drivers, and occasional drivers. Using discrete choice models, we modeled ride-hailing driver behavior throughout a 24-hour simulation day in 4 main steps to be able to understand and estimate how long the drivers work, when they start to work, and where they start their work within San Francisco's 981 traffic analyzed zones. Here are just a couple of examples for the modeling work that we have been doing and the output of the discrete choice models. We differentiated between drivers' primary, secondary, and tertiary shifts because during the observed data analysis stage, we found some differential patterns of behavior for the different shifts of the day. We don't have time to go into the details here, but this is just to provide with an example for the modeling output and our attempt to obtain models with a good fit to the observed data that will best represent ride-hailing driver behavior. With the results from discrete choice models, we use Python to generate San Francisco ride-hailing driver fleet. We are now working to compare the model driver fleet with the observed driver fleet. The figures here show an example of the compression between model shift start times and observed shift start times. For the driver start times, from the two upper figures, we can see similar pattern for the observed and model data, but there's still a disparity for which we are currently considering different options of how to make it even more similar. For the driver's shift duration, the model duration matches the observed duration quite nicely. For shift start location, we can also see a similar pattern for the modeled and observed data. This also shows us that ride-hailing drivers are more likely to start their shifts in the downtown area, which is what we expect. So far, we have completed 3 tasks: TNC data analysis, discrete choice modeling, and generating the San Francisco ride-hailing driver fleet and assessment. For the next step, we will generate a ride-hailing driver fleet for Salt City scenario based on the models we developed for San Francisco. We're already working on disseminating our work in the Conference on Advanced Systems in Public Transport and in peer-reviewed journals. Thank you for your attention. This includes my presentation for Project M3 on the multimodal optimization and simulation track.